Okay. See, from last week's study, we have already learned about the diagram of the circuit. So the diagram is basically the set of methodology of how to abstract a circuit into a graph consists of dot and lines. And in order to learn about the inner constraints between the dots and the lines, we have go over a little bit from the mathematical view of the topology. And from there, we come to this chapter. It's about several different but linked methods to solve the DC circuit problems. So far, we just learned a little about the DC circuit, very little, and we haven't learned about anything about the AC circuit. But in the later semester, we will gonna learn about it. Don't worry. We just go one step by another. And in this chapter, we focus several stuff: the branch current method, loop current method, node voltage method. This is the most important stuff. And we know that the very base of this stuff is coming from the KCL and KVL laws. And besides that, we have Ohm's law and other stuffs which illustrate the characteristic of the component, especially the voltage and current VI characteristic curve of the certain components. That will give us some extra constraints about the current and voltage in the branch. So we can use we can combine all these constraints together and list the equations. And from the circuit diagram, we just abstract a diagram into the diagram consists of dots and the lines between them. And from this stuff, we have learned how to transfer a certain circuit into one diagram, right? Consists of dots and lines between them. And from this inner constraints, we know we can calculate the branch numbers and the node numbers. And from there, we can find the inner constraint relationship between the branches and the nodes. So from last study, we have learned about this. So we don't go over every definition all over again. No, we know that. And from this definition, we know what is path, what is connected graph, and what is node, what is a branch, what is a mesh, and what is a loop. And we also know what is a tree and what is a subgraph. And we also know what is a linked or connected subgraph. And we also talk about the tree branches and other branches. So from this definition, we have learned about the branches and other stuff, connected branches and tree branches. So from this point, we have already gained a conclusion about the numbers between the nodes and the branches and the trees. So we know that the relationship between the numbers of the connected branches is b minus n minus 1. N is the number of the node. B is the total number of the branch. So b minus n minus 1 is connected branches. And we know that besides that, the n minus 1 is the tree number, tree branch number. And we learned about the definition of loop, right? Loop is a subgraph of a connected graph, and it forms a closed path or closure path. And is satisfied is connected, and every node linked to two branches. This is what is a loop. And from there, we have this conclusion. We know that to a graph, we have many loops, and the number of the basic loop is certain. So we're talking about the very number of the basic loop. So although the basic loop could not be identical all the same, but their number is certain. So their number is the continuous branches of the connected branches. And we also know that for a two-dimensional circuit or planar circuit, the number of the meshes is equal to the number of the basic loops. So, but for a three-dimensional circuit, that is not the case. But in our lecture, in our course, we don't talk about the three-dimensional circuit right now. So it doesn't matter. So it almost equal to the numbers. It always equal to the numbers of the basic loops. So we can use mesh current method, and we also could use loop method, loop current method. And so we can consider that the mesh current method is just a special case of loop current method. And we also know that the basic circuit is a tree with one branch connected. So the basic circuit has an exclusive branch. So once this basic loop basic loop takes this connected branch, and the other loop cannot take this branch any longer. So this is called the basic circuit or the single branch circuit. So we also reach this same conclusion that the number of the branches equals to the number of the tree branches plus the number of the connected branches. And we know that the number of the tree branches is the number of the nodes minus 1, and the number of the connected branches is the number of the basic loops. So we have this basic connection between them. This is what we have learned from last week. And we also give you several examples. We will not gonna go over these examples again. Not. And from this knowledge, we have gained the value knowledge of the independent number equations, a number of the independent equations of the KCL. So we also get the conclusion that for a circuit who has n nodes, the independent KCL equation number is n minus 1. So if you have n nodes, the independent KCL equation number is n minus 1. And then we talk about the basic, the number of the independent equations of KVL equations. So we can list the KVL equation, and we just deduct them, and we can reach the conclusion that we can prove that for the mesh equations we gained from this example, and we do it by adding and subjecting in the other options operations on these equations. We can gain the KVL equations from for other loops. So the conclusion is very certain. We know that the number of the independent KVL equations equals to the basic loop numbers, and A equals to B minus N minus 1. B is the number of the branches, and N is the number of the nodes. So the number of the independent KVL equations is B minus N minus 1. This is in directly from the very basis of the topology we have learned. So this is what we have known from last week's study. And for a circuit who has N node and B branch, the independent KCL and KVL equation is together will be B. So B is the number of the branches. And from this interconnection, we can conclude how to list the equations, KCL and KVL equations for any two-dimensional circuit, DC circuit. And first, we have learned about the branch current method, right? So we take the branch current from every branch as the unknown variable to list the equations about the inner relationship between the branch voltage and the branch currents. So we also know that we can pick any n-1 nodes to list a KCL equation for a circuit who has n nodes. And we can pick any b minus 1, b minus n minus 1 KVL equations from the basic loops columns. So this is what we have learned from last week's study, and we have some examples. So we're not gonna go over it all over again. So the general steps of the branch current method, I think you already know it. First thing first is to have to make sure we have the reference direction marked to each branch. And once you set the reference direction of the current voltage of each branch, during the following calculation, we will not gonna mess up. We will not alter that again. And we pick n-1 nodes and write this KCL equation, and we pick b minus n-1 loop to write the KVL branch equations. And this is what we have learned. We have learned the KVL equations. All the consumers together on the left side equals to all the producer voltage on the right side. And solve those equations above, we can gain the branch currents. And then you can further calculate the branch voltage and other stuff you would like to know. And we also know that the branch current is very direct and convenient, but it's not very extinct. It's not simple enough. So from there, we have learned about these examples. So then we learned about the mesh current method. In order to avoid the equation listing for all of the B branches, we don't have to worry about all the B branches. We only have to solve some mesh current. So we assume that the current continuously flow through the mesh, and we take those imaginary mesh current as unknown variables to list the circuit equations. So it's only useful to planar circuit. So the basic idea of that this method is we assume that for every mesh, or mesh is a special loop, and we have a mesh current, and all the other branch currents could be uh, uh, represented as the combination of the mesh current. This, this is how we use this kind of a methodology. And we do not go over this all over again. So this is basically what we have learned from last week's study. But something we have to pay attention that we know in this mesh current equations the self resistance is always positive, and the mutual or cross resistance could be negative and could be positive. It's according to the direction of the adjacent mesh current. So if two mesh currents share a branch and their direction is identical, we give it a positive and signal. And if they are going on the opposite direction, we give it a negative sign. So this is what we have to pay attention to. And we have learned a little examples. Then we learned about the loop current method. So this is what we have learned from last week's study. And we know that the mesh current method is basically a special case for loop current. And we know that the mesh is a very the basic loop, and the loop could be larger. And we also know that for a loop current method, to list a KVL equation, the equation number is b minus n minus 1, and is n minus 1 equations are less than the branch current method. And still, this example we have learned, we use this kind of a method to list the loop current equations. So in order to avoid complex combination of the current loop currents, in this case, we have learned from last week's study, we pick one loop to take as which contains the unknown loop current, and in the other one, we don't take the very adjacent small triangle, and we're using this rectangle, larger rectangle loop, and to avoid the listing on their common branch. So that this using this kind of a trick will avoid to make very complex cross resistance calculating. So this is a very basic trick we have learned from last week's study. And also, we know that we can list it like this. On the right side is all the sources we have learned, and on the right side is the consumer. So the and on the right side is the producer. left side is consumer, and the right side is producer or giver. We can also say that the left side is the taker, and the right side is the giver. And still, we have to pay attention to the sign of the self-resistance and the cross-resistance. The self-resistance is always positive, and the cross-resistance or the mutual resistance its sign is associated with the direction of the current, the loop current that runs through the common branches. And we also know that for two loops, their loop current may share more than one common branches. So this is what we pay attention to. We have to pay attention to this. So the basic steps of the loop method is to pick L equals to B minus N minus 1 independent loops, and we choose or we define their the circling direction of the current, loop current. And for L loops, we take the loop current as an unknown variable to list KVL equations. And by solving those equations, we can have the loop currents. And all the branch current could be deducted from the combination of the loop currents. And from the branch currents we have learned, we can calculate the corresponding branch voltage. So this is what we have learned about the last week's study, and I hope you have already mastered it. And the characteristic of the loop method is if you select the loops cunningly, we can reduce the amount of the calculation. But it also gives us some difficulty to recognize the cross resistance. So the cross resistor could not be sometimes could be omitted by mistake. So then the calculation will be totally wrong. And for the treatment of the ideal current source branch, we take if we have a current source, we choose the loop current to be the generally we choose the loop current to be the current of the current source. That will save us one equation. And if we have a voltage source, we also could use this kind of a relationship to do so. We can do it another way. Both are right. So, but in order to demonstrate this, we have to make sure that our equations should contain the voltage of the current source. So this is what we deal with about the ideal current source branch. So if you pick the current source current to be a loop current, you're going to save you some energy solving this the loop current of this loop. So directly we know that I2 is IS. And we also know that if you have a circuit that contains branches uh, which has control sources, uh, first we should consider the control source to be independent source. But we must add some supplementary equation to demonstration the UI relationship of the voltage and current relationship of the control source. So still we have learned about this example from last week's study. So this is basically what we have learned from last week's study. And I will go over it all over again. Now I think you have already mastered it. Right? So we can continue our journey for the very last part of this chapter, and in the afternoon, or probably we're gonna learn about next chapter. So for college course, our lecture, the total lecturing time is very limited, and to master it, you have to work all by yourself after the class. So if you don't go over the class, you probably will not gonna be able to master it. So it's not because it's so hard. It's not very hard, but we got too many stuff to remember, so to memorize. And if you don't do it uh, along with the course, sometimes you will be crushed if you with those too many those amount of knowledge. So in order to master it, we have to go over it all by ourselves and go to the textbook I give you, and you can using do some exercise from the textbook, and to master all these tricks and skills and methods we have learned. So let's continue our journey. This is not the voltage method we have not learned from last week's study. Obviously, our method is named after the variables the main variables we take as unknown variables for this method. So we take the node method, the node current voltage to be the unknown variable to list the equations. This method is suitable for circuit with not much nodes. If you have lots of nodes and but you don't have too much branches, this time you should take the branch current method to reduce the number of the unknown variables. But if you have a circuit with many branches but not many nodes, we can list we can use the node voltage method to avoid too many unknown variables. So what kind of solution you pick is up to you. And the basic principle is to reduce the numbers of the unknown variables, and to reduce the amount of the calculation to save some labor. This is a very basic principle. And it's very begin. And we see that the basic idea is very simple. If we choose the node voltage as the unknown variable, and it will satisfy the KVL equations immediately, and we don't have to list the KVL equations anymore. And all the branch currents and the branch voltage could be considered as the linear combination of the not voltage. Once we have solved, we have gained the node voltage, we can easily calculate the branch current and branch voltage in each branch by the combination of the voltage, node voltage. So let's see. Since we are doing the KCL equation, so the independent equation number is n minus 1. So the basic number of the independent equation is n minus 1. This is what we have learned from last week's study. And comparing with the branch current method, the numbers of equations, the number of the equations reduced by b minus n minus 1. So if how to select which method we will apply, you can do this calculation. If your if b is too much and n is very small, we can apply this kind of method. But if the b number is very small number and the n number is a very big one, we're probably not gonna select this kind of method, right? So what kind of method to select is up to you, but under those principles to save some labor. So there are many ways to solve a problem. Some may be harder, and we're probably not gonna select always the hard way. But this is a full human being. But if you have a computer, right, and you can you want to solve the problem by programming, and so the algorithm that looks different, very laboring for us, probably could be very simple for the computer. So in that case, we cannot. We're probably going to choose another way to solve it. So it's up to you if you want to solve the problem by yourself, or if you're using some simulation or other programming of the computer to solve this. So there's no certain way to decide which kind of method you should take, and so even if you don't have, you can't remember all this method we have learned, we still can solve the annual DC circuit by using the basic KCL and KVL method, right? And we can compare to the branch current method. We can well, this is not what we have learned, right? So we can pick the reference node randomly, and we take the node voltage as the voltage difference between the node we pick and the voltage between its voltage and the reference node voltage. So the difference between the voltage of the node we want to know and the reference the voltage of the reference node is so-called the node voltage, and this direction is pointing from the independent node to the reference node. See, let's see if we have this kind of a network here, and UA means the voltage of point A between point A and the ground point, and UB is the voltage difference between the point B and the ground point. And UA minus UB equals UB minus UA, and we add all the branches together, all three branches of this triangle together, and we have this conclusion. So it automatically satisfies the KVL constraints. And then we can list the equations, right? For example, we have this kind of a example. So we can select the reference direction, reference node, and then mark the voltage of the remaining n-1 independent nodes. So in this case, we can take this point as the reference point. So then we assume that the voltage on this point is 0, and all this then we only have 3 other nodes left. Note that this point is connected with this point directly with a wire, so they are the same point. So we only have 4 nodes in this circuit. And then we have 3 other nodes and a ground node. And so we can now we have selected reference node. Then we can list the KCL equations. We know that for each node, the current comes in equals to the combination of the currents comes in equals to the combinations of the currents come out. So total current come in equals to the total current comes out. So for point 1, we see that node 1, we have I1, I2, and IS and IS1 and IS2. This is a little too far. So there will not be some misunderstanding. Okay. So let's see that once we pick the reference direction, reference node, and we can list the KCL equations. For node 1, we have I1, I2 comes out, IS1, IS2 comes in, out, out, in, in. For node 2, we have I2 comes in, I3, I4 comes out. So give a negative sign for I2. For node 3, we have IS2 goes out, I5 goes out, and I3 goes in. So then we have this KCL equations for all the three nodes. And we also know that the independent number of the node which is 3. So we can express it with a node voltage to replace all the branch current, right? So we know that for the voltage of node 1, we know that the voltage equals to I1 times R1, right? So UN1 over R1 is a number of the I1, right? And UN1 minus UN2, U node 2, N is for node. U node 1 minus U node 2 is the voltage difference with over R2. So this is a I2. IS1, IS2 is a ideal current source, so we will not change it. Similarly, we can just replace all the other branch current with the node voltage. So we can do this process all over again, right? So we can transform these three equations into this kind of three equations, and we replace I1, I2, I3, I4, I5, 5 branch current, right? Well, 5 branch current. Five branch current into 3 node voltage, UN1, UN2, UN3. So in order to solve 5 unknown variables, now we only have to solve 3 unknown variables, right? So then we can transform this kind of 3 equations and do some simplification. We can just write it like this. The first equation, right, goes to this like this, and the second one is like this, and the third one is like this. So it's equations about unknown variables UN1, UN2, and UN3. So, and we also could see that in this case, US over R5 is an equivalent current source. So we do some equivalent transformation, right? You see that we have this one, and by rearranging the coefficients in this equation, we can see that this the US, the voltage source US is transformed into this kind of stuff, US over R5, just like the trick we have learned to transfer a series connected resistor and the voltage source into a current source and paralleled with a resistor, similar resistor, right? We have learned about this trick, all right? So we can using the same trick, but we didn't do it deliberately. It just automatically matches the trick we have learned before. And if we don't like the reverse of the resistance, we replace it with the conductance. So we can simplify this equations into this form. U11 times UN1 plus G12 times UN2 plus G13 times UN3, just like that. So let's take a 10 minutes break.
Laoshi, no, we can't hear you, Laoshi. We can't hear you.
All right, all right. Doesn't matter. Now you can hear me. You see that G11, G22, G33 are the diagonal coefficients of this matrix. So we see the diagonal coefficient is called self-conductance of each junction. So in this case, we have three junctions. So we have three diagonal coefficient. So we have three self-conductance. And the self-conductance of a node equals to the sum of all conductance of all branches connected to that node. So let's see. Let's see G1, let's see, is equals to G1 plus G2. So so this is a G1 and this is G2. And we can go back to the circuit. Let's see. For this node, we have G1 connected to it, G2 connected to it. And see, for this branch, as one branch, it doesn't contain any resistance. And also, neither does as2 branch. So there's only two resistor connected to it, and their reverse is a conductance. So G11 equals to the reverse and of R1 and the reverse of R2. And we can see that G11 equals G1 plus G2. And G22 is the self-conductance of junction 2. It's made up of G2, G3, G4. Let's see. Let's go back to the circuit. Let's see. And we see junction 2. The node 2 has R2 here, R4, and R3 here. The 3 resistor connected to it, and we have all the reverse of 3 resistors is we know that the reverse of the resistor is the conductance. So G2, G3, G4, right? Do you follow? And also we can see G33 is G3 plus G5. This is called the self-conductance of junction 3. So for this one, we have only R3, R5 connected to it. So we add all the branch resistance together to it. So the reverse of R3 plus reverse of R5 is equals to G3 plus G5, right? Like this one. So now we can self-conductance of each node, right? And G12 equals to G21 equals to negative G2. It's called the cross conductance or the mutual conductance between node 1 and node 2. Let's see. So this one is the G12, and this one is also G21. We can see this this matrix is well, let's say this matrix is symmetrical along the diagonal. So we can see this one, this coefficient is also appears in this direction. So it just looks like that. And also we can see that also we can go back to the now go back to the circuit, that we see that for node 1 and node 2, right, there's only one resistor between them. So the resistor R2 reverse is the conductance between them. So we have this stuff here. And we call it G12, and we also call it G21. So they are identical. So also we can do it with G23 and G32. Let's see what between node 3 and node 2. Between node 3 and node 2, there's only R3. So they got A minus the reverse, the negative reverse of R3. So we have this stuff here. And we also have this stuff here. They are identical. So the cross conductance or the mutual conductance is the sum of the conductance of all branches connected between nodes. So if there are two branches linked between node 2 and node 3, and we would add all the conductors, all those two, the conductors of those two branches, and their sum, we put a negative sign between their sum. So this is the cross conductance. So it's very easy to remember. And IS1 equals to IS minus plus IS2. So this is a algebraic sum of the current source current flowing into node 1. And IS node 3 equals to IS2 negative plus US over R5. So since the current of the current source IS2 is flowing out of the node 3, so we give it a negative sign. And the other one is the voltage source. So we're doing the trick that to replace, you see, the series connected resistance and the voltage source, and we transform into a parallel connected resistor and the current source. So we know the current source, the current equals to the voltage source's voltage over the its series connected resistance. So we could calculate like this. So we can see that for node 3, we have a IS2 flows out of it, right? And we have a US I5. I5 goes through it, and so we can transform this stuff into a series connected R5. So for this branch, node 3, we have a current source flows out of it, and we also have a R5 resistor paralleled with a current source. And the current source has a value of US over R5. So this is the trick we have learned to transform a series connected resistor with with a voltage source to a current source with a parallel connected resistance. So then we calculate us also have this one, this resistor R3. So for node 3, we have two current source flows in, right? IS2 flows out, and US over R5 flows in. So this is it. So this is the combining of all the current source, all equally transform the current source to it. So this is how we calculate the self-conductance for a node and the cross-conductance between the two nodes, and calculate the algebraic sum of the current source flows into one node. And if a node connected to a branch that contains only a voltage source, we're doing those trick to transform those voltage source to its equivalent current source form. So we still can use this kind of stuff to represent the total current from current source flows into one node. Flows in also means flows out, so we replace the current flows out of the node with a negative sign, so it also counts for flows in. So the inflow node takes positive sign, and outflow node takes negative sign. This is the definition. So once we have solved those equations and have the number of the node voltage, we can calculate the branch voltage, and the branch current could be represented by the combination of the branch voltage. For example, I1 equals to U0 1 over R1. I2 equals to UN1 minus UN2 over R2, and I3 equals to UN2 minus UN3 over R3. So on and so forth. We can have all those three. We can represent all five branch current with three node voltage. So in order to solve five equations for five branch currents, we only have to solve three equations for three voltages too, and we can also we can still have the number of the corresponding branch current that we would like to know. If we were not asked to solve that problem like this, we don't have to solve five equations. We only have to solve three equations to get the same results. And we can see the standard form of the node method equation, like this one. And all the coefficients from the diagonal coefficient, they are also called self-conductance. Its number is all the conductance combined that connected to that node, and we put them together. We add them all up to have a self-conductance. And it's always positive. And J and GJI is called self-conductance or cross-conductance, not self-conductance, or mutual conductance. It's always negative, and it's a combination of all the conductance together that linked both to those connected two nodes. This is how we do it, like this. And ISN1 Ni equals to all the currents from the current source that flows into the junction I combined. So if the current source current flows into the node I, we give it a positive sign. And if the current source flows out of the node I, we give it a negative sign. And we have to be aware that if that circuit does not contain any control source, the coefficient matrix is symmetrical to the diagonal. But if we contain such so-called the control sources, the situation will change. So we can summarize the general steps of the node method. First thing first, we have to choose the reference node and collaborating the n-1 independent nodes. So this is the first step. We choose a reference point and then we mark all the other left n-1 independent nodes, give each one of them a number. And the second step is to list the KCL equations for the rest each and every of the n-1 independent nodes. And three steps. The third step is to solve the equations we listed, and we can have the voltage of the n-1 nodes. So this is the typical step. And all the other branch currents, and we can calculate them by using the combination of the node voltage. This is how we do it. And then we can do other analysis. For example, like this one, we have a circuit that contains 4 nodes, and we take this node as a reference node, and we call it the ground. And we only have to write the equations about those 3 nodes. So for node 1, there are 1, 2, 3, 3 branches connected to it. And so we can calculate the self-conductance is G1, G2, G3, Gs. So its self-conductance is G1 plus G2 plus Gs. And the cross conductance between node 1 and 2 is, you can see, is G1. So G12 equals to G21 equals to negative G1. Right? And there's no direct link between G1 and G3, right? And we also see that for G2, for point 2, we have 3 branches linked to it. So G22 equals to G1 plus G3 plus G4. And we also already calculated G12 and equals G21. So we also know G21. So we only have to worry about G23. So G23 equals to G32 equals to negative G4. Right? And so on and so forth, we can calculate G33. There are only 2 branches connected to it, this one and this one. So it equals to G4 plus G5. Right? We can see that this is a G11, G1, G2, 3, Gs. And G12 equals G21 equals to negative G1. And I forgot about that this branch, right? This branch, they are connected, right? So G13 and G31 equals to negative GS. Okay, and this is it. I forgot about that. And the left side is the taker. We see that the right side is a giver. So the current that flows in to node 1, we can transform this one into a corresponding, you see, corresponding current source together with a right. So this is the green branch we have. And this conductance still GS. This inductance will not change, and the voltage source will have a value of GS times US. So this is for the first node 1, and we can just list the second the node voltage of the second node. So we see that G12 equals G12 equals to G21, so we can directly copy it, and we see that the G22 is the combination of 3, so we can just take it there, and there's only one conductance between node 2 and node 3. There's only G4. So there's no voltage source connected to it. So there's the right side of the equation is 0. Similarly, we can write this stuff to node 3. Node 3 is self-conductance is also forget about the green one. Must S2 GS, right? G4, G5, GS, right? Right. And we take this G13 directly to here. And we can take G23 to represent G32, since it's symmetrical. And the current, like this one, you see, is flowing out of G3. So the current is flowing out. So we give it a negative sign, negative E of US times GS. So this is how we list the voltage equations according to the standard form. So this is how we do it. So this is how we list the node voltage equations. And if we have a source that in one branch and is not associated with any resistance, a resistor, so how are we gonna do about it? So we have to get a supplementary equation by using the current of this voltage source. So and this time we see that we still have to write the node equation, node voltage equations. And we can see that for the first node, we can just you see, we just assume that the current that flows out of the voltage source is I, and we can treat it as a current source and to write the corresponding node voltage equations. And but we still don't know what the real number of the current is, so we have to get another extra equation to solve this problem, to solve this current I. So still, we have for node 1, we have G1, G2, 3 nodes, and there's only one branch between node 1 and node 2, that is minus negative G1. And there's only one current source flows in, so it's I. Then for node 2, we see that there are three branches connected to it. So its self-conductance is G1 plus G3 plus G4. And we just directly copy G12 here, right? And its self-conductance G1 plus G3 and G plus G4. And between nodes 2 and 3, we only have G4 here, so we put it here. And since there's no current source flows into it, so we give it right side a number 0. And similarly, we can write this for node 3. So for node 3, we see that you have 3 branches here, here, here. So its self-conductance is G4, G5. And we just directly copy this here. We have the connection between those two. And since this branch, the connected G1, G3, there's no resistance. We don't have a cross conductance between them. And the current source, the current flows out of G3, node 3 is I, so we give it a negative I here. So in this time we have an unknown variable U1, U2, and U3, and also we have an unknown current I. So this time we have 4 unknown variables and with 3 equations, so we cannot solve it. So we must think of some other tricks, right? So how to solve this stuff? Easy. We just transform this kind of a resistor grid, and we solve the current between in this US voltage source branch. We know that the difference, voltage difference between node 1 and node 3 is US, right? Right? So, and we also know that so this time we have 4 equations. 4 equations for 4 unknown variables, so we can solve this problem, right? So that's how we solve it. So we have to pay attention to the number of the unknown variables in the equations and the number of the equations. So if they don't match, we cannot solve that problem. Also, we can select the appropriate reference point. See, if we choose this point to be the ground point, and that leaves us 3 nodes above to list the KCL equations. We still have U1 equals to US directly. Since this point we take it as a voltage 0 point. So the number of the U1 is directly US. And we can also list all this KCL equations, and it's connected to 3 branches. So for this for the original method, we have to list this stuff, and for we see, we have to list this stuff to the first equation. But if we choose this point to be the ground zero point, we don't have to calculate US1, U1, because it's already known. So we only have to list the node voltage equations for node 3 and node 2. So we can directly list the node voltage equation for node 2 and node 3. So in this case, you see that the second method don't require us to have a supplementary equation to solve this problem, because we choose this point to be the ground zero. So still 1, 2, 3 is 3 unknown equations, and 3 unknown variables and 3 equations sufficient enough to solve this problem. So let's talk about the circuit that contains the control source branch. For those kind of circuits, we should list the equations considering the control source to be the independent sources, and we represent the control the control variable with the node voltage. So similar to how we treat the control source in the loop current method, we do it like this. For example, let's write node voltage equations in this circuit. Since we only have 2 nodes, so it's very simple. Only 2 to write, and we select this part to be the ground zero. So for the first node 1, I have 3 branch connected to it, so it's very easy. Its self-conductance is the reverse of R1 plus the reverse of R2, and the cross point between R1 and R2 is R1. So its self-conductance is the reverse of R1. All right, and the current source IS1 flows into the voltage, the node 1, so we give it a positive sign. And for the second node, node 2, we have 1, 2, 3, 4 branches, and its self-conductance is R1, reverse of R1 plus reverse of R3, and we also know is the cross conductance to node 1 is the negative of the reverse of R1. And we take the control source as a independent source. So since its current flows out of node 2, so we give it a negative sign. And also the ideal or current source flows out of it, we give it a negative sign. So this time we still have something to solve because we only have two equations for three unknown variables. Since this UR1 we still don't know, so we have to write about this stuff. UR1 is simple. Since we select this point to be ground zero, so UR1 we see that UR1 equals to UR1. So we can replace this UR1 with this UR1. So then you have two equations for two unknown variables. So this is a definition of how to list the node voltage equations according to its standard form. The only thing we have to there are only three things we have to remember, that we have to notice every cross conductance. In the first example, I have gotten about one branch that happens all the time. If you encounter the situation that dealing with so many branches. So the second one is if you have a voltage source, independent voltage source in your branch, then how you gonna do it? You just either you choose the reference point direct wisely to avoid calculating, otherwise you have to assume you have to put another unknown variable of into the equation. That is the current of the independent voltage source. And the third thing is if you have control source in loop in the circuit, we would like to know is to treat the source control source as the independent source firstly to list the equation, and we have to find some supplementary extra equation to solve the extra unknown variable, like the current or the controlled current or voltage of the control branch. So this is three stuff where we have to pay attention to. Let's see another example. Let's see note the voltage equation of this circuit. In this circuit, we have 1, 2, 3, 4 nodes. So we have 4 nodes. How many branches we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 branches. So if you list, if you use the branch current method to solve this problem, you're gonna need to solve 8 equations for 8 unknown variables. But if you list the node voltage equations, there are only 3 unknown variables, and you only have to find 3 independent equations to solve this problem. So in this case, if you have the number of the branch is way larger than the number of the nodes, so this time obviously you should choose the node voltage method. So let's see. First thing first, we have to find a reference point. So in this case, we select this point to be a reference point. And we have only 3 nodes left. And we treat the control source to be the independent source, and then we find some supplementary equations. So we see that un1 directly is U equals to Ri. Ri is the voltage of the controlled voltage source. So we don't have to list the corresponding voltage, the node voltage equation for node 1. So then we can do it directly to node 2. Node 2 connected to 1, 2, 3, 4, 5 branches. So its self-conductance is the reverse of R1 plus reverse of R2 plus reverse of R4. And there's only one branch connected to point 1 and one branch connected to point 3. So we see that the reverse of R1, negative reverse of R1 is a cross conductance between 1 and 2, and the negative reverse of R4 is the conductance, cross conductance between 2 and 3. And there are two current source flows in point 2. And we see IS1 goes out, so we give a negative sign, and G3 goes in, we give it a positive sign. So we still have to list another for the node 3. So it contained it is connected to 4 branches. So its self-conductance is reverse of R5, reverse of R3, reverse of R4 together. And since this branch connected 1 and 3, so we give it negative reverse of R5, and this branch connected 2 and 3. So we give it a negative sign, R4. And we also have this current source flows out of it. So we know that we will give it a negative sign. And also we can replace this stuff, this ideal voltage source, and with current source, with a current like this. And it also flows out of node 3. So we give it a negative sign. So, but this time we still don't know the value of I. So we have to see the value of I, and we also have to find the value of U3, right? And we know that U3 is the difference between U2 and U3. So we know that U3 minus U2 is U. That is not correct, right? U3 is directly here. We have this U3. So we only have to find it, know it. U3 is U3, UN3. And U3 is UN3. And we have to find the other control source, I, R times I. And we also know that I equals to UN2 over here, over R2. So I is the current of this branch, R2 branch. So we have listed 2 supplementary equations for this stuff. So now we have 5 equations for 5 unknown variables. So this is how we list the node voltage equation for this example. So from this morning's lesson, we have learned, we have reviewed what we have learned the methods before the last week, and we also learned about we also introduced you the node voltage method. And we have to remember that all these methods came directly from the KCL, KVL equations. So if you don't remember any of this stuff, you still can list the KCL and KVL equations from the very beginning. So I don't. If you can remember that, you can still using some other tricks to solve the problems, but it's probably not going to be that that efficient. So, but it still that will still do the job, right? Okay. So much for this morning. See you in the afternoon.
OK，老师，拜。
OK，老师，拜。